Okay, so we have looked at the notion of analyticity. We have been looking at functions of a complex variable. We have seen some properties that analyticity endows a function with. There are many more properties which we will also discuss as we go along. But analyticity is a nice thing to have, right? So it's it allows us to make general statements about functions. Functions which are analytic have certain nice properties in the region of analyticity, and therefore it's a desirable thing to endow a function with. So in this lecture, we will look at how the exponential function, which is something which we define for real variables to start off, and how the exponential function can be generalized for complex variables, keeping in mind the requirement or the desirability of making it an analytic generalization. Right? So we will look at how to start with the exponential function for a real variable and generalize it so that it remains analytic in as large a region as possible. We will also look at a similar exercise in the context of many other functions as we go along. But in this lecture, it's all about the exponential function. Okay, so we are all familiar with the Euler formula. So it says that e to the I theta is equal to cos theta plus I sin theta, and one argument to see how this comes about is to write down this Taylor expansion on the left hand side. So e to the I theta, if you expand it, and so you blindly take the argument to be I theta, and then you collect all the real terms and the imaginary terms separately, and you can sort of argue that the series corresponding to cosine theta will be the real part, and the series corresponding to sine theta will be the imaginary part, right? So this is one way to come up with a justification for this formula, right? So in this lecture, we will look at how starting from the idea of an exponential of a real variable, if we wish to generalize this function to apply it on complex numbers, how can we do this in such a way that we have analyticity for this function in as large a region as possible, right? So in general, when we are generalizing functions to to include complex variables, there are two requirements. One is to ensure that the function reduces to the same function that we're used to when you, instead of a complex number, you put a real variable. So if you have z equal to x plus iy, and if you put y equal to 0, it must give back the original function, right? So this is a absolute minimum requirement. Otherwise, you wouldn't even call it a valid generalization. But also, we would require require the condition, or include the condition that the generalized function is analytic in as large a region as possible. So let's see how, if we try to do this with the exponential function, we can actually sort of get another alternate way of a justification for this Euler formula. Okay, so we start with the function e to the x, where x is a real variable, and then we ask, how can we give meaning to the function f of z is equal to e to the z, where z is x plus iy, right? So we start by demanding that this function too should have this familiar property, e to the x1 plus x2 is equal to e to the x1 times e to the x2. So we're going to give meaning to this e to the z, but we also expect that this function will also satisfy this kind of a property. So we should be able to write e to the x plus iy as e to the x times e to the iy. Right? So e to the x is the same e to the x that we already know. It's just exponential of a real variable. Now e to the iy is where we have to provide meaning for this quantity e to the iy. So it has a real part and an imaginary part. So we can think of this real part as some function g1 of y, right? So it is necessarily a function only of y because the input is only y, and then it has an imaginary part which is g2 of y. right? So as far as this function f of z is concerned, so this function also has a real part and an imaginary part, right? So which we are used to thinking of as u of x comma y and v of x comma y. These are the real parts and imaginary parts. But here this u of x comma y and v of x comma y have this special form. So it should be u of x comma y must be of the form e to the x times g1 of y, and v of x comma y is of the form e to the x times g2 of y. Now these functions g1 of y and g2 of y must also satisfy this property that when you put y equal to 0, g1 of 0 must go to 1 and g2 of 0 must go to 0, right? Only if this happens would we get back e to the x when y is 0, right? So this is also a an essential requirement in our bid to get a valid generalization of the exponential. So now we want this resulting function to be analytic in as large a region as possible. So if this function is analytic, then it must satisfy Cauchy-Riemann conditions. So we have u of x comma y is e to the x times g1 of y, and v of x comma y is e to the x times g2 of y. And if you plug in the Cauchy-Riemann conditions with for these two functions u and v, we must impose the conditions dou by dou x of e to the x times g1 of y must be equal to dou by dou y of e to the x times g2 of y, and also dou by dou y of e to the x times g1 of y must be equal to minus dou by dou x of e to the x times g2 of y. Right? So if we carry out these partial derivatives, so this is an differentiation with respect to x, so it's just e to the x, and so you get left hand side is e to the x times g1 of y, and the right hand side e to the x is for all practical purposes just a constant as far as this partial derivative is concerned, so you can pull it out, and then dou by dou y will become d by dy because g2 is a pure function of y, so you have e to the x times dg2 by dy, and then the second equation becomes e to the x times g1 dg1 by dy must be equal to minus e to the x times g2 of y, right? So if we combine these two conditions, so e to the x will cancel throughout, so g1 of y is equal to dg2 by dy, but g2 of y is minus dg1 by dy. So if you take the derivative, so you get d squared g1 by dy squared is equal to minus g1, and likewise if you take the derivative of with respect to y in the first equation, then you get d squared g2 by dy is equal to d g1 by dy, but gd(g1 by dy is the same as minus g2. So indeed both of these have the same second order equations which we know how to solve, right? So this is nothing but the simple harmonic oscillator problem. So the solutions are either cos y or sin y or some arbitrary linear combination, except in this case it's not quite arbitrary because we are given that g1 of 0 must be equal to 1 and g2 of 0 must be equal to 0, right? So that comes from this requirement that this function, the generalization will reduce to just exponential x when we put y equal to 0. So if we do this, so we can write down immediately that g1 of y must be equal to cos y and g2 of y is equal to sin y. Therefore, a natural generalization for the exponential as we go from exponential of a real number to exponential of a complex number is to say e to the z is e to the x times cosine of y plus I times sine of y. Now if you put x equal to 0, of course, so this will immediately give us the Euler formula basically. So it's the statement that e to the I theta or iy in this case. So in place of e to the z you have e to the iy, this is cos y plus I sin y. So this is a way to argue for the Euler formula, right? So it's a generalization of the exponential function, such that the generalization is analytic. In fact, it turns out that this function e to the z is analytic in the entire finite complex plane. So there are no singularities anywhere in the finite complex plane. So it's an entire function. So we have achieved both our goals, and to the extent which is possible, the maximum extent possible. So we have got an entire function, so it's very nice. And so there are some properties of exponential functions that we take for granted, but we will state it here, which, well, I mean, can be verified using these first principles, right? So this definition, so if you take e to the z1 times e to the z2, it's the same as whether you do e to the z2 times e to the z1, and that is the same as e to the z1 plus z2. Again, e to the z1 divided by e to the z2 is e to the z1 minus z2, and 1 over e to the z is e to the minus z, right? So these all follow from this definition of the exponential of a complex number. And then we can also take the derivative of this function. It's an analytic function everywhere. It's an entire function, so the derivative is well defined everywhere in the complex plane, finite complex plane. And so if you take the derivative, so we have seen that the value of the derivative is just given by dou u by dou x plus I times dou v by dou y. So in this case, it's just going to turn out to be e to the x times cos y plus I times e to the x times sine y, which you can pull out the e to the x, and then you can rewrite cos y plus I sine y, and then you just identify that this function is nothing but e to the z, right? So if you take the derivative of the exponential function with respect to z, right, it's evidently not dependent on z star, so it's analytic everywhere, and so the derivative is well defined, and its value is the same as the value we have given to the function itself, so which is very nice. So we see that not only does the function get a valid generalization, but its derivative formula also looks the same, as if we are working with function of a real variable, right? So these are all properties which are familiar from properties of exponential of a real variable, but there are also some properties of the generalized function exponential of a complex number which are a bit counterintuitive. So let's look at some of these. One is that it turns out that this exponential of z is actually a periodic function, right? So we don't think of the exponential as a periodic function, but when you generalize it, so you have e to the z plus 2 pi I is the same as e to the z times e to the 2 pi I, and e to the 2 pi I is 1. So we find that in fact e to the z is periodic with a pure imaginary period of 2 pi I. So you can add any integral multiple of 2 pi I to your z, and if you take the exponential of this number, you get back the same answer as for the original complex number itself. So in fact, the exponential function is a periodic function in the complex plane. So another property of e to the z that's not there for e to the x is that e to the z can also be negative, right? So in general it can be a complex number, and in fact it can also be negative, right? So this gives the magic formula e to the, this is seen in the magic formula e to the I pi is equal to -1, right? So which is the famous formula which connects all the fundamental mathematical constants. Also, in fact, you can find a complex number such that e to the such a complex number is whatever complex number you want, not just a negative one, but in fact given any complex number z0, it's possible to find a complex number whose exponential is z0, right? So this is a statement we'll just make here, but this is the seed of how to find such a complex number whose exponential will be a given complex number. If you go further in that direction, that will lead us to the next function, which we will discuss in detail in a separate lecture, that namely the logarithmic function. But as far as this lecture is concerned, the focus is on the exponential function, and that's all for this lecture. Thank you.